So today we're going to look at lesson 6 from unit 2, properties of linear functions and linear models. We're just going to do a couple of examples that are involved in this lesson. So in this assignment, we're going to really focus on what we refer to as linear functions and their properties. Remember, there are three views of a function. We had the equation, the table, and the graph. We're mainly going to focus on the table today. So remember, a linear function by definition is just going to be f of x equals y mx plus b. This comes from, if you recall, from our earlier lesson, y equals mx plus b was a linear equation. But now we're using function notation. We're using the f of x instead of the y. And remember, the coefficient m represents what we describe as the slope. Remember, slope is that rise over run, the change in y over the change in x. And the y-intercept, this constant b, is the y-intercept. And remember, x was 0, and when x is 0, wherever the line crosses the y-axis would be called the y-intercept. As far as the table view, again, that's the big T, the T-chart. That's what we're going to kind of look at a little bit today. Like I said, in the last section, we worked with various functions, but really we're just going to look at tables today. And we're going to look at these tables and we're going to determine if the table actually represents a linear function. And one of the keys is when you look at a table, we're looking for if the slope exists. Slope is what's referred to as the ratio that describes the rate of change. In other words, we have this delta y over delta of x, which really means the change in y over the change in x, or in other words, y2 take away y1 over x2 take away x1. That's how we actually determine the slope, is look at that change, that ratio. So it's kind of what we're going to be looking at here in a couple of tables. So we're going to be given this table down here, and we're going to try to determine if this table actually represents a function. To do that, what we're looking for is this constant change in the y values and also with the x values. If there isn't, then the table does not represent a linear function. So let's look at this table and let's determine if it is a linear function. And if it is, we actually want to determine the slope using the change in y over the change in x ratio. One of the things you have to pay attention to is to determine the rate of change, your order pairs have to be in some order. And what you have to look at is your x's. They have to be in either like a smaller to larger or larger to smaller order. And we kind of see this is going from smaller to larger. So now I can actually interpret to see if this table represents a linear function. Notice how it goes from a -2 to a -1. That's an increase of 1. -1 to a 0, that's also an increase of 1. 0 to 1, that's an increase of 1. 1 to 2, that's an increase of 1. So there is this constant change in the x's. So what has to happen is there has to be this constant change in the y's. So now if you go from a 4 to a 1, that's a decrease of 3. If you go from a 1 to a -2, that would also be a decrease of 3. If you go from a -2 to a -5, that would be a decrease of 3. And a -5 to a -8, that would be a decrease of 3. So this would be a linear function. So the slope is going to be the change in y, which we said is -3, over the change in x, which is 1. So your slope is actually going to be, we use letter M there. Your slope is just going to be then this -3. So yeah, that does represent a linear function. Now, you can also use subtraction, and if the change remains the same, then it is a linear function. So on my y values, if you're not recognizing the change, you could just go 4 minus 1. That would give you this 3. 1 take away a -2. So that's really a 1 and a 2. A 1 and a 2 would give you a 3. And a -2 take away a -5. Notice I have a -2 and a -5. I'm sorry, the opposite of a -5. So it's going to be a -2 and a 5. And that's also going to be a 3. So notice how the change is remaining constant. But over here, we have to pay attention to the direction as well. the change is actually going down 3. But there is this constant value that we're seeing. So that kind of verifies, yes, we do have a linear function. Look at this next table. Notice how again it goes from a -2 to a -1, a -1 to a 0 to a 1, and a 1 to 2. So those are going in from an ascending order, from smallest to largest. So a -2 to a -1, that would be increasing by 1. A -1 to 0 would be increasing by 1. 0 to 1 is increasing by 1, and 1 to 2 is increasing by 1. So there is this constant change in the x's. What has to also happen is there's got to be this constant change in the y's. So from a -8 to a -3, that would be an increase of 5. A -3 to a 0, that would be an increase of 3. This is not going to be a constant change. So this does not represent a linear function. So this is going to be not linear because we're not seeing that constant change in the x values with respect to the y values. So we won't be able to find a slope either since it does not represent a linear function. So next thing we're going to do is we're going to create an equation of a linear function. So a cost function, the simplest cost function is called a linear cost function. And it's going to be denoted by c of x equals the c of x plus b, where the y-intercept is going to represent the fixed cost. And the slope is going to represent the cost of each item. So suppose that a small bicycle manufacturer has a daily fixed cost of $1,800 and each bike costs $90 to manufacture. Write a linear model that represents the cost of manufacturing bicycles each day. So C is going to represent the cost and the X is going to represent the number of bicycles, or the C should represent the total cost, and the X is going to represent the number of bicycles made each day. Now, from what we picked up on, the B is going to be the fixed cost. Well, they said the fixed cost was this 1,800. So it's going to be your B. Your B is going to be this 1,800. The M is the cost of each item. Well, each item costs $90. So M would be this 90. So I can't create the cost function. So the cost function is going to be C of X equals 90X plus this 1,800. So it's going to be our cost one. If I want to graph this model, you can graph it on the calculator, but also we can kind of try to do this by hand as well. So I'm going to kind of try to draw the axes. So I have the x-axis and the y-axis. So I'm graphing this, you know, my y-intercept's 1,800, so I have to count by something. I'm gonna use 600s as a way to get there. So 600, 1,200, 1,800, 2,400. So if I count by 600s, 600, 1,200, 1,800, and 2,400. As far as the bikes goes, you know, we may just say, let's just count by tens. So 10, 20, 30, 40 bikes. So to graph it though, we need basically 2 points. So the 1,800 is one of the points already given to us. So we have the 1,800 given. Now to find another point, let's just use 10 as an X value. So when I make my table, you know, the 0 gave me the 1,800 because that was the y-intercept. Let's just use 10 and see what we come up with for that. So 10, I'm going to have 90 times 10, which would be 900 plus 1,800. So 900 plus 1,800 is going to be my total cost at that point. So 1,800 and 900 So we're going to have this 2,700. So I'll probably need another tick mark there. And that's going to be like 3,000. So 2,700 would be somewhere in between there. So 10 and 2,700 would probably be halfway. Oops, this is a little lighter color there. So it looks like 2,700 would be about there, halfway. So then I could kind of sketch my graph through here. And that would be my graph. The cost of 14 bikes, if I use my graph, 14 looks like it's going to be right around 3,000 or so, if I'm guessing. But to get a more accurate answer, what I'm going to do is just solve this algebraically. So since we're giving you what the number of bikes is, we can actually multiply 90 times 14, and we can add the 1,800 in, and that's going to allow us to determine the total cost. In other words, the cost when 14 bikes are made is going to equal 90 times 14 plus 1,800. So 90 times 14, again, you can do this on a calculator. I'm going to try to do this by hand. We'll see what kind of trouble I'll get into. 14 times 90. Looks like 1,260. And then I have to add 1,800 to that. So 1,800 and this 1,260. So it looks like 3,060. So that's about what I was predicting off of my graph. So if 14 bikes are being made, it's going to cost the manufacturer $3,600 because of the fixed cost of $1,800 and $90 per each bike being made. So that would be C would be 30,000, or say 3,060. I'm sorry. So $3,060. How many bicycles could the manufacturer be made? How many bicycles could be manufactured for $3,780? So here it looks like they're giving us the cost, and we're trying to find the number of bikes. So to solve this, it looks like they're giving us we're basically looking for what X is, and we know what the output is. So our equation would become then 90X plus this 1,800. And we know what the cost is now. They're saying that's 3,780. So now we're trying to find what X is given what the Y value was, or the output value. So to solve this, we have to lose 18 on each side, 1,800. So 3,780 take away 1,800. I'm getting brave here doing this math by hand. I haven't done that in a while. So it looks like I'm getting 1980. So 90X is going to equal this 1980. And I got to divide both sides by 90. So 90 going into 1980. So 90 would go into 198 twice. 2 times 90 would be 180. That'd be 180. 90 times what gives me 180 would be a 2 again. So it looks like 22. So 22 bicycles could be made for $3,780. So that kind of completes this lesson here. Just a kind of short lesson on just linear models. Hopefully that helps a little bit with your homework.